Alright, welcome folks. This is a little bit of a bonus video for the probability material. Specifically, we're going to look a little bit at how sampling distributions work by demonstrating a few of them, creating them from scratch. So remember, the purpose of the sampling distribution is to account for the fact that variability is reduced when we're comparing sample means to a population mean based on how many people are in the sample. More people, less variability, even though the mean stays the same. We use this sampling distribution to account for that. The effect it has on our calculations is we convert that standard deviation to a standard error that accounts for the sample size and for the fact that variability is dropping in these sampling distributions. So some other basics. Again, the idea of a sampling distribution, we're drawing an infinite number of random samples, all of the same size, all from the same population. We're going to place their sample means on that distribution and see what the shape of it is. So there's a link here. It's available in the PowerPoint slides that are downloadable on the sampling distribution video. But here I'm going to demonstrate that little applet for you, and let's bring it on over here. So here's what you get if you click on the link. There's a little begin here. There's some instructions there. But basically, to explain it to you, what we've got here is a raw score distribution. And it starts off following a normal curve. We can set it to some other stuff. And when we click the button, it's going to draw a sample of, in this case, 5 people, but we can change it, all from that sample, all from the population, and place the sample mean down here. You do that enough times, eventually you're going to get a distribution of sample means here. So let's draw the biggest sample possible, because those are the most likely to form a normal curve, and let's do a couple of animated samples. First, I want you to note a couple things. The mean of this original distribution is 16, the standard deviation is 5. So it's going to draw 25 scores completely at random. Most of them are near average. Some of them are a little bit farther away. Drawing 25 people, all from that population. And when it's done, there's the mean of that sample. That's the mean of a single random sample. Let's do one more animated, and then we'll start speeding things up. So again, we're drawing another random sample of 25 people. There are the individual scores, and there's the sample mean. Still pretty similar. So let's speed it up a bit. Again, we will skip past watching it all being visualized there. We can take 100,000 samples all at once. So let's take a nice, say a cool 500,000 samples, all again of 25 people drawn at random from this population. So we now have 500,002 sample means that have been placed on this sampling distribution. Couple of things to note about it. Notice it's much narrower than the original raw score population was. It's compressed. The variability has dropped. Scores are clustered much more tightly around that population mean. Also notice the mean. It was 16 originally. It's still 16. Standard deviation, though, has dropped from 5 to 1. By the way, if you plug these numbers into that standard error formula, 5 divided by the square root of our sample size, which is 25, you would get 1. It has exactly the standard error you would predict. So that's true for the normal curve, but one of the interesting things about the sampling distribution is how it always forms a normal curve. So let's do a non-normal distribution. It'll make some stuff that's skewed here. Let's again take 500,000 samples now from this skewed distribution. What direction is it skewed in? Positive. So 500,000 samples. Couple of things to notice again. Notice this is a normal distribution, and it's still much narrower, but it's almost perfectly symmetrical. So the mean is still the same, 8.08. The standard deviation has dropped from 6.22 to 1.25, and again, that's what you'd get if you plugged it into the formula. And again, what used to be a skewed distribution in terms of the raw scores has now again become a almost perfect normal curve. If you got an infinite number of scores, it would be perfect. It's very close with 500,000. Let's do something really funky, and let's look at a distribution that is nowhere near normal. We can actually draw this stuff with a mouse. So let's make something that's kind of trimodally here. So yeah, that looks pretty good. All right, is that sufficiently non-normal for you? That's a hot mess of a distribution there. Let's again clear this sampling distribution. Let's look at some basics. The mean of 14.78. The standard deviation is a little below 10. Let's take 500,000 samples again. And again, notice it's very close to a normal curve. Notice that it's narrower than that original distribution. And notice that while the mean has stayed the same, the standard deviation has again dropped. It's about 1/5 of what it was. So the big takeaways here, Those sampling distributions always turn into normal curves with a big enough sample size, as long as you draw enough samples, and they always wind up with the same mean as the original distribution and a much smaller measure of variability, the standard error. Again, notice that the shift from standard deviation to the standard error down here is exactly what you'd get from our formulas. So play around with that applet a little bit, do some other demonstrations. This will really give you a better conceptual sense of what it means to create this sampling distribution and how it tends to affect our key descriptive stats. For now, you can move on to that practice quiz.